Hello. You might have noticed that this is not Minecraft. This is instead Scrap Mechanic. Today I'll be continuing this series on videos that aren't Minecraft because the server ended quite a while ago. But today I'd like to teach you guys something very interesting, and it's how to build a CPU using logic gates. Now, if you're like the average person, you might not have ever heard of a logic gate before. So in this first video, I'm going to discuss some very basic concepts dealing with how this game would do a CPU and the different basic components we're going to need to build it. Upon hearing about these logic gates, you may be wondering what they are. So, in the game here is one logic gate. This is very simply just a block within the game. Now, inside this block, you can choose up to 6 different types, and that's what I'm going to be going over today. So, if I get a light like this one, and I rotate it so it's the right way, and I take my connection tool. Now this will draw connections between things. If I draw the output to the light turns off because this is not activated. Now, if I turn the switch on, which will turn this on, turns the light on. It's quite simple. So, the AND gate is this one right here. It's this design. And what this means is that if you have 2 connections here, it will only activate if both of them are on. For example, it's not on. It's not on now, and it's not on now. But only once both are active, the light turns on. Now the next type of logic gate is OR. What this means is if any of the inputs are on, it will be on, but that does not limit having all of them on. Now you could possibly do this with more than 2, but for simplicity, I'll just use 2. Now you have the third type is XOR. Now, this one is the same as the last one. If you have one input on, it's on, but if you have both of them on, it turns off, as well as having both of them on. Now, when would you use this, you might ask? Well, in the game Scrap Mechanic, there's one major use for this type of logic gate if you haven't played the game. The major creation that this is used in for most Scrap Mechanic players is for a door. Now let's say you have a hypothetical door here, and you have one switch on the outside of the door. You flip the switch, opens the door. Now once you're in here, and you close the door, it's like that. And then you can open it from this side. But what if you have the other side on, and this side's off, but you want to close the door? Well, you just flip it like that. Now this circuit is 2 switches going to this XOR gate here, to the controller, and to the bearing, which tells it to go 90 degrees after I just corrected it. Now, anybody who's played Scrap Mechanic for a decent length of time will probably be familiar with building something like this. But it's the same concept for just the logic gate. I just built that to help explain it. Now, the next type of logic gate is a NAND gate. Now, this one is inverting the output of the NAND gate, of the AND gate. I use this mostly to just invert things, but it can have other uses. Now, the NOR gate is active when none of them are on, but not when one of them are on, but also not when both of them are on. Now, the last type of logic gate Scrap Mechanic has is the XNOR gate. This one is my new favorite one, because what it does is with the two inputs we have here, if one of them were to be different from the other, if they were different inputs, like right now they're both off, it outputs an on signal. And if they're both on, it also outputs an on signal. But if they're different, only then will it turn on. This will come in handy later. Now that the basics are out of the way, it's time to see some circuits that you can build with these. So, the number one circuit that I use the most is called the latch. And here's the image of what the circuit diagram looks like. Now, how you go about building this is quite interesting. Now, in scrap mechanics, you can't connect the logic gate back to itself. That's the very important thing. And if you looked at the circuit, you have a NOR gate and a NOR gate. Now, if you wanted to start building a loop for that, you draw this to here, but then you can't connect this to here without reconnecting it how real computers would. So what I do, and it causes a bit of complexity, but it's okay. I take the output of this one back into that one. Now, this creates what is known as a memory bit, or an SR latch. Now, this one can toggle it on and off at the press of a button. But for a computer to send pulses to this, for it to do things, a button won't do. So, after you have your circuit like this, your memory bit, and this little triangle shape, you need to have two AND gates, which will act as sort of like the thing that allows the button presses to go through. And you connect them to the same place I had the buttons. So now you have it like that. And then, let's say, for this example, you have your button, which connects to both AND gates as to only allow an output when it is ready to go. So next thing is you're going to need a switch, and that's going to be your data signal. But if you want it to be able to turn off the thing, how are you going to make it so one of them's inverted? Well, I like to use a NOR gate for that. So you connect the switch to the NOR gate. The NOR gate goes to one of the AND gates, and the switch goes directly to the other. I have that backwards. It would connect this way, because turning it off would want to reset it. And a way you can tell what the actual value is by the OR gate in the middle. Now what this circuit does is you can have this switch be whatever data you want. But only when you push the button does it allow that data to go through. And by doing this, you have a SR latch, also known as a set reset latch. And you can store 1 bit of data now. If you're not at all familiar with computers and how they work, a bit is simply one on or off signal of data. Now, computers like to store these in chunks of data. So, for example, you have 16-bit, 8-bit, 64-bit, and 32-bit. You might have heard of your computer being 64-bit, and you might have heard of like 8-bit sound or like textures or things. Now, how you would do stuff like this is quite simple. The width of your data changes. That's all it is. Now, if you're building a CPU and scrap mechanic that uses this, you're going to have a very fun time, because that's a lot of connections. The next most important thing about the CPU is that this circuit can be built much smaller. So I build the D latch here, and I have my switch here, and my button here, and I connect the button to those, and I invert the switch on that one, and I drag that one to this one, and I also drag the switch directly to that one. It does look complicated, but this is the exact same circuit as before. And I construct a little loop for this. You now can connect those to there, and you now have a much smaller D-latch, also known as a logic bit, because it uses logic to store one bit of information. Now, let's say you wanted to build an 8-bit storage device. How would you do that? Well, I have already built one. Here is my previously saved 8-bit version of this storage data. Now, 8 bits is equal to 1 byte, and the only difference between this one and the last one, well, besides being 8 times larger, is this little output one here. This line of outputs, you can allow it to output it only when that gray one is activated. But here, you can have whatever data you want, then it only goes through once you press that, once you add an input to here. And like I said, you can output it here. Now you may look at this and say, hey, what's the black one for? Well, the black one is reset. Now, that can be useful in some circumstances, but the most useful one is definitely the fact that in Scrap Mechanic, when you place down a logic bit directly off the lift, it starts to flash. Now, that's just a quirk of how the game works. Real logic gates don't do that, but I usually have a circuit that I'll discuss later that automatically presses that black button here. Now, if I'm just going to put this back on the board here and rebuild the board a little. Now that we have our way of storing data, the next most crucial circuit to build is what's known as a binary decoder. Now, if you've heard a little about binary, or like don't know much about binary, you've probably not built a binary decoder. Now, let me explain what a binary decoder does. Is what it takes is, let's say, a 4-bit binary signal, which can go through numbers 0 to 15, and it outputs it at 15 different outputs. There's the 15 outputs. Now, how would you get from here to here with the binary number being converted into an output? Well, if you have your switches and you have the output, it's very simple how you would build one of these. Is that you also take an inverted output of that and you connect your switches to both the non-inverted and the inverted output of that. Using the NAND gate and the AND gate, the NAND gate just inverts the AND gate. But since there's only one input for each of these, all they do is just have it on or off. Now your first option would be 0, because this goes through 0 through 15 because it is 4 bits. Now what you want to do is you're going to want to take all the ones that are on for each binary number and connect it to the respective output gate. Now for 0, connect all these to this AND gate, which means that only when all these are on, because they're inverted, which means when all these are off, that will be on. Now, if you look at the binary number 1, you do the same thing. You take all the ones that are on, which is three inverted outputs, which means when 3 are off, and 1 normal output, which means when that one's on, you get a 1. So now you can toggle between 0 and 1. Now you take the number 2 in binary, and you run your same outputs here, all the ones that are on, directly to the output, and then you keep going. Like for example 3, you take all the ones that are on and connect them. Now you have 0 to 3. You got 0, 1, 2, and 3. Now you would keep going all the way to 16, but that's going to take a while to show off. Here is a more complex but complete version of the 4-bit binary decoder. Here's the person that made it. You can find this on the Steam Workshop for Scrap Mechanic, probably. Now, this does the same thing, just a bit differently than my design does. And what this does is for every single one, it takes the inverted and not inverted version of it, just from the 4 inputs. Now you got your 1, 2, 3, 4, and then, you know, it keeps going all the way to 15. Now you might be sitting here wondering, how do I count in binary at all? Well, that's the next thing I'm going to teach. It's actually quite simple. Let's take these, let's take inside this little square I've made. Each row of this wood is one number. Now, 0 would be all off, because binary you have on and off. Now, let's say you want to do 1. In the first bit, that would be on. Now, for 2, if you add 1 to it, that turns to 0, and this turns to 1, now you have 2. And then you add 1 more to it, and you have 3. But now that you add 1 more, it's got to roll over. So now you have 4, 5, 6, and 7. Now if you notice, a pattern starts to form of this little, I don't even know, whatever shape this is. But this is easily replicatable, and it's kind of simple to do. Now, the way I learned binary was through about a year of working on these. I don't have 1,300 hours on this game for no reason. It's because I work on CPUs and things. Even I have trouble remembering binary numbers sometimes. But you'll get the hang of it if you do start working with it. Now the next component that's important is an adder. Now I'll confess, I've never actually built an adder circuit. Here's a diagram of what it looks like. And how it works is you have 3 inputs, actually. But if you're doing bit number 1, you would have just 2. So you got your 2 numbers you're going to add together. You do 1 and 1. Yeah, of course I can wire that right. You got your 1 and your 1. Actually, like I said, I've never built one. So here's a slice of 1. You got your 1, and you got your 1. But how binary works is if you wanna do it properly, and you do 1 plus 0, that would be 1. If you do 1 plus 1, that'd be 0 with a 1 to the left. And that's what this AND gate on the end does. And then you wire that into this AND gate here for the next one. Now here's a 8-bit adder, and here's the person that made it. This is the one I always use, and it works quite simply. And you can add binary numbers, like 1 and 1 is 2, 1 and 2 is 3, and you can keep going, like 1 and 7 is 8. Like that. But you might be wondering, once you get to the end, what happens? This is the carry bit. It just says that you overflowed your number. Now, this is useful in a lot of things. Most important, you probably guessed, would be adding. That makes a lot of sense. So, once you get the hang of the numbers in binary, this stuff comes very easily. Now that I've discussed all the basic things in Scrap Mechanic that you would do to use logic gates to do things, is next thing you would want to do is you would want to make your own stuff using these circuits. But before you start, there's a very important thing to know. And you can tell this by looking inside a timer. Now in a timer, it tells you that 1 second in game is equal to 40 ticks. Now each change in logic, for each logic gate to change over time, takes 1 tick, and that means you can have 40 of them change in a second. And that might not sound like a lot, but once you have CPUs like mine which had 4,937 logic gates on it, that would take quite a while to change. So you just got to remember that you can add delay of a few ticks or even a few seconds between things happening just by adding a timer. I'll add a button here, and you see after that delay, stuff happens. And it's quite simple. And the timer, the binary decoder, which is this thing, and the adder, which is this thing, are three necessary components for computers in scrap mechanic. Now you might say, but a timer is just one block. Well, it can be the difference between your stuff working and not. Just like knowing how to use each of the logic gates here. And if you actually have the game, sorry I didn't mention this earlier, but it does tell you a bit of an explanation. But I gave an explanation because I thought for XNOR it wasn't really useful. So just remember for XNOR that it's just when they're the same it has an output, and when they're different it doesn't. Well, thank you for watching this video. The next video will cover how to turn these simple circuits, including the latch, also known as like a logic bit, and then the adder and the binary decoder. Next video will cover how to turn those into RAM, the basic form of RAM. And then we might get started on a CPU next video. Thanks for watching.